In Theorem 6, we can see that if the series is convergent, then we can say that the limit as n approaches infinity of that series is equal to 0. Now the proof would state that if we have the sum of those series, which is a subscript 1 all the way to a subscript n, then a subscript n is going to equal s subscript n minus n subscript n minus 1. And since we know that this series is convergent, the sequence is convergent. So if we let the limit as n approaches infinity of s subscript n equal s, and then since n minus 1 approaches infinity, as n approaches infinity, then we also have the limit of s subscript n minus 1, which is equal to s. And therefore, the limit as n approaches infinity of this series is equal to the limit as n approaches infinity of s subscript n minus s subscript n minus 1, which is n equal to the limit as n approaches infinity of s subscript n minus the limit as n approaches infinity of s subscript n minus 1. Well, that means you get s minus s, which is going to give us 0. Now let's note 1. With any series, we associate two sequences: the sequence of its partial sums and the sequence of its terms. If we know the sum of that sequence is convergent, then the limit of that sequence is s, which is the sum of the series, and as Theorem 6 asserts, the limit of the sequence is going to be 0. Now note too that the converse of Theorem 6 is not true in general. If the limit as n approaches infinity of that sequence is equal to 0, we cannot conclude that that sum is convergent. Observe that for the harmonic series 1 over n, we have a subscript n, which is equal to 1 over n approaches 0 as n approaches infinity, but we showed in example 1 that it was divergent. Which brings us to Theorem 7, which is the test for divergence. If the limit of that series does not exist, or if the limit does not equal 0, then the series is divergent. Now the test for divergence follows from Theorem 6 because if the series is not divergent, then it is convergent, and so the limit is going to equal 0. So in example 8, we're going to use the test for divergence. We want to show that this series diverges. So we're taking the limit as n approaches infinity of that series, and then what we want to do is we're going to multiply both the numerator and denominator by 1 over n squared. We get the limit as n approaches infinity of 1 over 5 plus 4 over n squared. We're going to get 1 over 5 plus 0, which is 1/5. Now since 1/5 does not equal 0, then we can say that the series diverges by the test for divergence. Now note 3 that if we find that the limit of that series does not equal 0, then we know that that sum of that series is divergent. If we find that the limit is equal to 0, then we know nothing about the convergence or divergence of that series. Remember the warning in note 2. If the limit of that series is equal to 0, the series might converge or it might diverge.